It's important to realize that these vectors that we have in Lorentz space over here, is regular space-time, dx, y, z, these things made with two spinners, these vectors, these are straight. Now, they could be pointing any which way. You know, they could be straight, perpendicular, parallel, crossing, anything. But this is Lorentz space where everything is straight. In Lorentz space, we need vectors. So that's what these half-half things are. This is a vector, this is another vector. Now we can cross them together like this, and we can get different fields out of that. So we can get the spin 2 field, we can get two different spin 1 fields, and then we can get a spin 0 field. This is a spin 0, this kind of looks like spin 1, and this is kind of what spin 2 would look like. Now Lorentz space is just spin 1, 3, and that makes sense. We've got time and 3 space. But let's look at this 10-dimensional space here. It's like a spin 1, 9. So we can have this thing called a Hodge dual. We're kind of missing the spin 6 over here, and well, this is kind of what we could consider Lorentz space, and some kind of a Hilbert space would go over here. Now this is a legitimate breakdown mathematically, but does it really represent our universe? What we need to do is essentially attach a copy of this X helix thing like this at each point. So it's no longer the straight lines, but rather it's some twisted version of it. Now, why do I want this double X helix like this? Why is that so important? I mean, let's look at, for example, Holiday DNA junctions. This is, if we have a shape like this, like a DNA strands, that gives us so much information because look, we can take the different DNA proteins like A, T, C, and G, and we can flip them around and give them different kind of rules where we can exchange each other, just like particle physics. The problem is, this X helix is not enough to be able to break this down exactly as I drew this here, where we can kind of get this U1, SU2, and SU3. This doesn't really work that way. Theoretically, intuitively, it should, but not mathematically. Now, it's actually quite a coincidence that if we have 4 spinner strands, 4 times 4, we're going to get this strange number count, which is 10 plus 6. And so we actually need this spin 6 and this 10-dimensional space over here. And when we do that, then we can see how like the spin 6 essentially is the same thing as having 4 spinner strands. 1, 2, 3, 4. So we have this SU4. And what's really crazy is that we can call one of these strands a non-vanishing spinner. So it always has to be present and it never vanishes. And the other 3 strands can just kind of be off here to the side and do their thing. Because J squared equals -1 means that we could do a Wick rotation, time equals imaginary time, and then we can also assign these pairs over here, these coordinate pairs, where J squared is equal to -1 for them as well. We could go ahead and move this into the coordinate system of imaginary coordinates, and we can kind of get 3 complex coordinates, pluses and minuses. So we basically derive this Calabi-Yau threefold geometrically from this structure. Yes, this is correct geometrically. However, the group theory here, this does not contain the SU2 group. So if we look over here, we're going to notice that we have this diagonal thing. This is a hypercharge generator. So we have 1/3, 1/3, 1/3, and then a -1. So the only thing we can really get with a 4-dimensional group is going to be that 4 splits up into 3 plus 1. And if we have the third right here, we're going to assign it a 1/3 charge. And over here we get a 1, but that's a -1. So these are really the only 2 things that pop out of this group decomposition. So if SU4 is not the correct decomposition, then what is? Well, in 1974, these guys over here, Georgi and Glashow, they discovered that SU5 grand unified theory. So we had to start with the spin 10 and break that into 2 5s, and then one of those 5s can break into 3, 2, 1. So we have 5 dimensions. That means we have this 5-dimensional generator here, 3 1/3 here, and 2 1/2. So we can actually say that 3 times 1 plus 1 times 2, that just equals 5. Okay, 3 plus 2 is 5. And then we just noticed that we have 3 of these, so we have a color triplet, and we have a weak singlet. That's just a 1 there. And over here we have a color singlet and a weak doublet in terms of the SU2. And you can see they just borrowed their charges. You got -1/3, and then you got +1/2. So that's what we could stick into the 5, and we could break it apart, and all that nice stuff comes out. You could do the same thing with 10, basically double it. And here you have a color triplet with a weak doublet over here. Essentially what we're doing is we're adding negative 1/3 plus 1/2, and that gives us 1/6. And then over here, we could take the anti-triplet, weak singlet, and we basically get 2 of these equals negative 2/3. Over here, we have the 1, 1, which is basically just saying that you can take both of those two and add them together as well, and you get 1. So you get a color singlet with a weak singlet. Now, all these things here are just quark charges and quantum numbers, so it basically just describes the standard model of particle physics just right there with 5s and 10s. This would be a perfect theory, but the proton has been shown to decay at a different rate than what was predicted. And so that's why we have to look at other theories, get into bigger groups, and try to break things down from a larger group structure, because unfortunately these small group structures just don't really predict exactly what's necessary.